Example number 3. This one definitely looks different than the first two. Why? Well, because you're not given the solution region right out of the gate. You're just given the system of linear inequalities here. You're given what's called a linear programming problem, and you have to be able to graph these inequalities within a coordinate plane system, and then based upon your graph, then determine whatever the maximum value is. Okay? So let's go ahead and get started. First thing we have to do is figure out how to graph these two inequalities. At least that's what I'm going to do first. So I'm going to come up with my intercepts first, which would be 15, 0, and then 0, 5. And we already looked at how to do this back in section 6.1. So now in the second linear inequality, my intercepts would be what? They would be 4, 0 and 0, 16. This information, x is greater than or equal to 0, y is greater than or equal to 0. This just means that our solution will be located in quadrant number 1. Okay, so let's go ahead and begin to graph this feasible region. So what I've done so far is I've plotted a y-intercept from one of my inequalities and an x-intercept from another one of my inequalities, and I've labeled the origin. That's going to be one of my corners or vertices in this feasible region. But before I do anything else, I'm going to think, based upon these intercepts I came up with, think about this, 15, 0, 0, 5. 15, 0, 0, 5. 15, 0 would be off the page based upon how I have this thing drawn. And because the inequality symbol is less than in both of these, that would mean that you're going to be shading below the line, okay? In other words, if I use the test point 0, 0, wouldn't you get 0 is less than or equal to 15, which is a true statement? Because it's a true statement, because both of these are less than or equal to, then the shaded area will be below the line. And in the other line, we came up with 4, 0 and 0, 16. That would look something like that. And again, it would be shaded to the left or below the line. So because I know that, I'm not going to graph anything yet until I do the following. And that would be to now look at this as a system of linear equations, these two inequalities. Look at them as a system of linear equations and solve this to determine the point of intersection, because we're pretty confident that a point of intersection is going to occur. Well, where would it occur? Well, let's find out. Let's multiply the top equation by -4 and see what we get. We'd get -4x minus 12y equals -60. And the second equation would stay the same. And it would be equal to that. And now let's go ahead and add using columns. So, what are we going to get here? We're going to get 11y is equal to what? Well, it'd be -11y. Jeez, is equal to what? -44? Yeah, so therefore y is +4. So if y is +4, just plug it back into one of the original equations. Let's say this equation. If y is 4, what would x have to be to make this true? Well, if y is 4, then x would have to be 3, right? So because why? 4 times 3 is 12. 12 plus 4, that's 16, which is equal to 16. So that makes sense. So again, you have to be able to determine any points of intersection that exist between the graphs of two linear equations, because you may have to use that point as a corner point, as a vertex. All right, so now that we know that we do have another vertex occurring here at 3, 4, I'm going to put this point on my graph. So let's go ahead and do that now. So 3, 4 would be, there's 3, and then 1, 2, 3, 4, looks like that. And now again, because I know that this line would be about right there where my pen is and shaded below it, and the other line would look like this now, connecting those two dots, and shaded below it or to the left, I can now graph in I can now complete the graph of this particular linear programming problem. So it would look something like this. Just connect the dots there. And then I'm going to connect the dots here. And so the feasible region would be right here. This is our feasible region S. Okay, and let's label our last corner or vertex, and that would be at 3, 4. Okay, so that's really the hard part, I guess, about these types of problems. You don't just get the solution region, all right? That's not given to you, okay? You have to figure it out. Now all you're gonna do is the same thing we've been doing, and that is you have your vertex column, and then you have your objective model column, which in this case is P equaling 3x minus 4y. And so what I'm gonna do is put all the vertices in here, just like this. And then I'm just going to use substitution again, just like I did in the first two examples, guys. It's exactly the same thing now as it was in the first two examples. So 0, 5 would give me a negative 20. And let's see, 3, 4 would give me a negative 7, I think. If you plug in a 3 here and a 4 there, that would yield a negative 7. 4, 0 would give me a 12, right? And 0, 0 would give me, well, 0. So again, we're trying to maximize this. That's what it's stated. That's what it's stating in the example. Maximize this objective function. So whatever the largest value is, that is the answer, okay? So 12 is the maximum value based upon this vertice in this particular linear programming problem.